For the case where we have a pipe of R over L small, so we have a relatively long pipe compared to the radius of the pipe, and for which the Peclet number is large relative to 1. We understand that the non-dimensional energy equation is of this form. We understand that the first term here represents the physics of fluid flow, and the term on the right-hand side represents the physics of diffusive or conductive heat transfer. The solution of this problem would provide us theta as a function of axial distance z and radial distance s. We know that this is a map in a dimensional sense to t of x r. The way this problem is solved is actually by separation of variables, and so in separation of variables sense, we could identify that theta should be separated into a function of z multiplied by a function of s. Using sort of standard separation of variables techniques, and all that means is that we're simply thinking of d theta dz as this z prime s and d theta ds as s prime z, where the primes represent the derivative with respect to either z or s, that we go through that process and we get a mixed problem in terms of derivatives of the s variable and of the z variable. By dividing through by s capital Z, we get two differential equations, two ordinary differential equations, one in terms of z and one in terms of s. So using standard ideas in separation of variables, there's an eigenvalue problem that's been set up, and the eigenvalue for this is, as we've done in other types of problems, is given this notation lambda squared. So lambda is the eigenvalue, lambda squared is this coefficient that we're using over there. So we note that the sign is negative, and the reason for that negative sign is we want oscillating functions in the s direction, and it'll also give us an exponential decay in the axial direction. So you're not responsible for the details of this. This is quite complicated actually, but it's good to know where this comes from. So again, two ODEs are defined in terms of the s and the z variables. We integrate the z dependence to get that there's an exponential decay in the axial coordinate, and there's a method called a power series method called the method of Frobenius to solve for the s function. And that s function is actually in terms of a power series, in terms of the, either you think about it as the radial coordinate s, or in terms of, remember that s is equal to little r over capital R. So this form for s is inserted into the ODE. We get roots of it, and the infinite series solution is sometimes denoted in terms of what are called the Gretz function, and we are calling that Gretz function Rn of s here. So this Frobenius method, just to put it in context, is the same way that that one would identify or generate a lot of different functions in mathematical analysis, and these include things like Bessel functions, Laguerre polynomials, Legendre polynomials, etc. So there are a lot of different, many different differential equations that come up in mathematical physics and engineering. This Frobenius method is a very general way of finding out what the solutions are. Some very well-known functions. If you Google Bessel, Laguerre, or Legendre, you would find lots of details on it. In the heat transfer context and in convection in pipe flow, the Gretz function is similar in principle in terms of how we generate it to these other types of solutions. Okay, so the composite solution, the full solution of theta in terms of z and s, is this power series. This generalized Fourier series. So it's a generalized Fourier series where the Gretz function R and S are the orthogonal functions, the basis functions, or sometimes called the eigenfunctions. And the family of lambdas that allow this to satisfy the boundary conditions are, again, the eigenvalues. So one of the things that we know about solutions of this type is that after a relatively short distance, the exponential attenuation of this means that subsequent Rn, subsequent Gretz functions, are no longer needed. That is, in some sense, that we can truncate this series, this generalized Fourier series, to, for example, a single term. So after a short distance, the exponential terms wipe out the higher Gretz functions, the higher Rn's, and if we were just to retain two terms, that means that the third term is small, and we can show that relatively easily. What is particularly interesting about this is that when we look at this third term expansion, that two-term expansion with the third term small, it really is a suggestion that that this is how we might determine what it means to be fully developed in a thermal sense. So the thermal fully developed is a truncation of the Gretz function to really a one or two term approximation. So it means a smooth temperature profile. And I like to think about it perhaps in a sort of almost in a simpler way. The way I like to think about it is that if theta were just using a single term expansion, so if we were just using a single term expansion, you basically have A0 exponential of in x and this R0 in S or R. So let's just make this like this. And for a fully developed profile, and we'll talk about this shortly, it means that when you look at, for example, the average temperature or average temperature difference between the wall and the mean, so like a mean temperature, which is an axial, it's average in a cross-sectional sense, a cross-sectional area sense, this thing is only a function of z. So the mean temperature, sometimes called the bulk temperature, so this is a bulk excess temperature, is only a function of z because, you know, it's true across the whole cross section of the pipe. So if I have a profile where theta z of s divided by theta m of z is not dependent on z, then I know that this thing is fully developed. So mathematically, you can think about it as the denominator here has the whole z dependence in a simple way, and it matches the z dependence in the numerator. Physically, you can think about it that all the axial variation is embodied in the bulk temperature, and all we're doing is identifying what the radial structure is by having this non-dimensional profile.